Hello, and welcome to AP Physics at Lyons Township High School. I got another example of curve straightening for you. This one involves free fall. So here's the deal. You're given data on different planets, okay? And so you travel to 3 different planets and you start at Earth. And you measure the gravitational acceleration on each planet, and you drop a rock from the same height on each planet. And you time how long it takes the rock to hit the ground. So somehow you measure the time with a timer or a watch, and you measure the gravitational field at each planet, okay? And what we're going to determine is that our goal in this problem is to figure out from what constant height did you drop all 4 rocks, okay? And we're going to use curve straightening to figure that out, okay? So yes, you could take these and plug them into an equation and get a height for each one, but it's more accurate to actually use curve straightening to get that height, okay? So what you might want to do is copy down that data, okay? And I've also graphed G versus time, okay? And you might want to go, you don't have to copy that down. You could do it in your calculator if you wanted to. But if you did graph G versus time, this would be the graph that you would get for that particular data. So I'll pause the video for a sec, or you pause the video for a second, and if you go ahead and copy that down. Okay, we're back. All right, so here's the deal. You'll notice that this relationship is not linear, okay, between gravity and time. It's a curve. And it could be one of 2 things. It can either be inverse or it can be inverse squared. So we're going to have to figure that out by using our formulas of motion. Now this we do know, okay? So we're dropping all these things, all 4 of these rocks, from the same height. Okay, so that's delta y. So we know an equation that involves delta y, time, and the acceleration of gravity. And that equation is delta y equals v naught t plus 1/2 a t squared. We're dropping these from rest, so v naught is 0, okay? A is simply g, and delta y is this constant height that we're dropping these rocks from. So if I rewrite this, height equals g over 2t squared. Now, on the y-axis there, I've got g. So we're going to get g by itself, okay? That's the goal. Whenever you have a graph of y versus x, get y by itself in this equation. So if I get g by itself in this equation, okay, you get the following. You get 2h over t squared, okay? Now, what should we graph involving time to get us a straight line, okay? Well, another way to write this is g equals 2h times 1 over t squared. Same thing, okay? It's a different way of writing it. All right, so what are we going to graph? Well, we're still going to graph g. I'm not going to change the y-axis at all. And on the x-axis, we're going to graph 1 over time squared, okay? So, all right, I've already sketched out a graph. I didn't change the y-axis. That's g, okay? On the x-axis, we're going to put 1 over time squared, okay? So real quick, we'll make a third data column, and that's going to be 1 over t squared. The units will be 1 over second squared. Whatever you do to the variable, you do to the units, okay? Now I've already calculated these out. You can save yourself the trouble. If I do 1 over this squared each time, for this one I get about 2.5. For this one I get about 6.5. For this one, I get about 0.94, and for this one, I get about 3.8. Okay, so those are my 1 over time squared values. I'm just flipping this over and squaring it. Okay, all right. So now we're going to graph those. So, and I got tick marks every one. So this is 2, 4, and 6. The biggest 1 over t squared gets is 6.5. I went ahead and went to 8 here. So a couple notes about the graph. Your axes should be linear, meaning every tick mark should be the same value. In this case, the g changes by 5 each time, and in this case, each tick mark is 1, okay? Each axis needs to be labeled with what it is. So here I've got g, the acceleration of gravity, and here's the units. On the x-axis, I'm graphing 1 over t squared. Now, a common mistake would be, okay, the units are seconds. Nope. It's 1 over seconds squared. So the units are 1 over seconds squared. Okay. All right, and our 5 points were, the first one is 2.5, that's about here, comma 9.8, that's about here or so. Okay, the second one was 6.5, comma 26. So 6.5 is there, 26 is about there. Third one is 0.94, comma 3.8, just under 1. And it'd be about there, so, okay. And the last one is 3.8, comma 15, so just before 4. And 15, so right about there. Okay. Now, if you're using grid paper or a calculator or Microsoft Excel or something, you're getting a better graph than I'm doing here. I'm sketching this by hand. But I think we'll be reasonably adequate here. All right, so I'm going to draw my best fit line, which for me is about there. Okay, and again, not perfect, but we'll go with it. Okay, I'm going to find the slope of that best fit line. Okay, and again, I'm going to pick 2 points that are not data points. So I'll pick I'll pick here, about there. So that's 2, comma 9, maybe. Yeah, we'll call it 2, comma 9. That's 1 point. The other one I'll do farther away. So let's do 7, about there, comma. Let's see, I'll make sure I'm 7, comma, I don't know, 29. So 7, comma 29. Okay. Now again, if you're using graph paper or a calculator or some, you're going to probably get slightly more accurate results than me, but hey, good enough. Okay. All right. So there's my 2 points. A note: the 2 points I pick on the graph, they're not very close together. You want them, really as far apart as you reasonably can pick. That reduces error. So the further apart the 2 points are that you pick, the better. Okay. So our slope is rise. Well, I went from 9 to 29, so the rise is 20. And the run, I went from 2 to 7, which is 5. Oh, so our slope is real simple. It's 4. Okay, now technically, you probably should put 4.0 or something, but hey, we'll call 4. And what are the units? Okay, well, you do rise over run. So we've got meters per second squared divided by 1 over second squared. Okay. Now we're going to reduce that. You can multiply both the numerator of that fraction and the denominator of that fraction by second squared, and they drop out. And so our slope is 4 meters. Now, the original question we asked was, from what height are you dropping this rock every time? A tendency is to go, oh, hey, look, I got my meters. Oh, I'm done. It's 4 meters. That's the answer. No, it's close, but not quite. Okay. I'm going to rewrite the equation that we were using here. We were using g equals 2h times 1 over t squared. Okay? You graphed g versus 1 over t squared. Okay? What's the slope of our line represent? Well, the slope is whatever's left in the equation when you've graphed this versus this. Well, what's left? 2h. Okay, that's the slope of your line. So the slope equals 2h. Our slope is 4, and that equals 2 times h. So the height is 2 meters. So each time we dropped this rock, it was always from a height of 2 meters. So that's another example of curve straightening. Again, a couple notes, a summary. Graph your original data or put it in a calculator and figure out what's the mathematical relationship between those 2 bits of data. For us, it was inverse squared. Okay, g is inverse squared proportional to time. G is proportional to 1 over time squared. So then what we're going to graph are those 2 things, g versus 1 over time squared. Make sure you label both axes. You put the units on both axes. You make sure that your axes have a linear scale on each side. That means the tick marks are equally spaced. You graph your points. You draw your best fit line with a straight edge. Even I use a straight edge even for this sketch. Write down the 2 points you're using this for the slope. Okay, what are they? Calculate your slope like in Algebra 1. And then also calculate or figure out the units of your slope. This is just as important as the number. They're equally important. So we got our slope, and then we figure out, like, well, hey, how does our slope relate to what we're trying to figure out? Well, we're trying to figure out h, and our slope is 2h. So there you go. So those are the steps you use in curve straightening, and that works every time on every example. So we hope that was helpful, and thank you very much.